Long before self-propelled forage harvesters became standard equipment across Europe, silage production was one of the slowest and most exhausting operations on a livestock farm. Through the 1950s and into the 1960s, dairy herds were growing steadily, especially in West Germany, France, and the Low Countries. Farmers needed more fermented feed to sustain higher milk yields during winter months, yet the machines available at the time were still heavily dependent on tractor power, manual labor, and small field working patterns developed decades earlier. Most forage harvesting systems relied on pull-type choppers connected behind relatively modest tractors. These machines could cut grass or maize, but their throughput was limited. Wet material clogged easily, knife systems required constant adjustment. Operators spent long days clearing blocked feed channels, while trailers waited motionless in muddy fields.
During peak harvest weeks, entire farms revolved around the timing of forage collection. If rain arrived at the wrong moment, nutritional quality dropped quickly. The problem became more severe as farms expanded. Larger cattle operations demanded faster harvesting windows, but adding more workers was becoming difficult and expensive. Rural labor shortages were beginning to appear across Western Europe as industrial jobs attracted younger generations away from agriculture. Farmers no longer needed slightly better machines. They needed an entirely different harvesting system. Manufacturers understood the pressure. Companies across Europe experimented with higher capacity forage equipment, but many early concepts remained too heavy, too complicated, or too unreliable for everyday farm use. The industry was waiting for a machine that could combine mobility, cutting power, and continuous throughput into one compact unit. That pressure would eventually create the conditions for the arrival of the Claas Jaguar 60SF. By the late 1960s, forage harvesting had become a race against time. European dairy farms were increasing in scale, but the machinery supporting them still belonged to an earlier agricultural era. Tractor-mounted and pull-type forage choppers remained common across thousands of farms, yet they struggled to keep pace with modern feeding demands. Even powerful tractors of the period often lacked the consistent horsepower required for heavy silage operations in wet conditions. Farmers faced the same frustrations every season. A field could look manageable in dry weather, then become nearly impossible after several days of rain. Pull-type machines lost efficiency in mud because the tractor had to provide both traction and harvesting power simultaneously. When crop density increased, feed rollers slowed, cutting quality suffered, and the flow of material became inconsistent. Silage production depended not only on machinery, but also on perfect timing and ideal weather conditions that rarely lasted long enough. The economics were becoming dangerous. Delayed harvesting reduced feed quality, which directly affected the milk output during winter. Poorly chopped silage fermented unevenly inside storage bunkers. Entire herds could suffer nutritional losses because harvesting equipment could not maintain stable cutting performance during critical weeks. Some manufacturers attempted larger pull-type systems with wider headers and more aggressive feed mechanisms. Others experimented with semi-mounted machines or multiple tractor combinations. But these solutions introduced new problems: higher fuel consumption, greater mechanical stress, and increased operator fatigue. In many cases, farms needed additional workers simply to keep the harvesting process moving continuously. Agriculture was beginning to industrialize, yet forage harvesting remained trapped between old farming methods and rising production demands. The industry needed a machine designed specifically for silage work from the ground up, not another adaptation of tractor-based equipment. That realization would push engineers at Claas toward a far more radical idea. Inside the engineering departments of Claas, the growing crisis in forage harvesting was impossible to ignore. The company had already earned a strong reputation in combine harvesters, but silage production represented a different challenge entirely.
Grain harvesting operated within relatively predictable seasonal windows. Forage harvesting demanded continuous throughput, high moisture tolerance, and the ability to survive unstable ground conditions for long working days without interruption. Engineers studying field operations noticed a fundamental limitation in conventional forage systems.
Tractor-based machines divided power between propulsion and harvesting. In difficult terrain, especially wet maize fields, the tractor often lost efficiency before the chopping mechanism reached its full productive capacity. Increasing tractor size only solved part of the problem. The machine itself still depended on external power delivery and complex towing geometry. The solution emerging at Claas was controversial for its time: a compact, self-propelled forage harvester built specifically around continuous crop flow. Instead of adapting an existing tractor system, the entire machine would function as an integrated harvesting platform. Engine placement, operator visibility, feed channels, and discharge systems would all revolve around maintaining uninterrupted material movement. This concept eventually evolved into early Jaguar series development, including the Claas Jaguar 60SF. Compared with many agricultural machines of the era, it looked unusually specialized. Its proportions were different from conventional tractors. The cab position emphasized forward visibility. The intake and chopping systems dominated the machine's structure. Nearly every design decision prioritized harvesting efficiency over traditional agricultural styling. The idea carried enormous risk. Self-propelled forage harvesters were expensive, mechanically complex, and unfamiliar to many farmers. Some believed smaller European farms would never justify such dedicated equipment. But Claas engineers understood something critical before much of the industry did. Silage harvesting was no longer a supporting farm task. It was becoming an industrial process. When the Claas Jaguar 60SF first appeared in fields, many farmers did not immediately see it as the future of harvesting. To operators accustomed to tractors with attached implements, the machine looked oddly unbalanced. Its body was dominated by the intake and chopping assembly, while the cab sat high with unusually direct forward visibility. The discharge spout curved above the machine like industrial processing equipment rather than traditional farm machinery. But every unusual design choice served a practical purpose. The Jaguar 60SF was engineered around crop flow efficiency. Instead of pulling material through multiple external driveline systems, the machine directed power internally from a centrally designed harvesting platform. Feed rollers pulled forage steadily toward the chopping drum, reducing interruptions that commonly affected pull-type systems. Continuous material movement was critical because inconsistent feeding reduced chop quality and increased mechanical stress. Its self-propelled layout also transformed mobility. In muddy silage conditions, operators no longer depended entirely on a separate tractor's balance between traction and PTO power delivery. The machine's weight distribution and dedicated drive system improved the stability during difficult harvesting periods, especially in wet maize fields where older equipment often struggled. The cab itself represented another important shift. Earlier harvesting systems forced operators to constantly monitor side-mounted implements or trailers from awkward positions. The Jaguar's elevated visibility improved control over crop intake and discharge direction. During long harvesting days, this reduced operator fatigue and improved coordination with transport vehicles moving alongside the harvester. Still, skepticism remained widespread. Many farmers saw the machine as overly specialized and expensive. Smaller operations questioned whether such a dedicated harvester could justify its cost compared to multipurpose tractors already working on the farm year-round. Yet, as harvesting seasons continued, something important became impossible to ignore. The Jaguar 60SF was finishing silage work dramatically faster than many conventional systems around it. Beneath its unconventional appearance, the Claas Jaguar 60SF was fundamentally a machine designed to solve one engineering problem:
maintaining constant harvesting flow under unstable field conditions. Every major component reflected that priority. The machine used a diesel engine delivering power levels considered substantial for forage equipment of its era, generally within the range expected for medium self-propelled harvesters of the late 1960s and early 1970s. Unlike tractor power systems, engine output could be directed specifically toward chopping performance and machine movement without competing through external PTO arrangements. This gave operators more stable harvesting behavior during heavy crop loads. At the front, pickup systems and crop headers fed material into compression rollers designed to regulate intake before chopping began.
Consistent feeding was critical because forage quality depended heavily on chop uniformity. Uneven cutting created fermentation problems inside silage storage structures, reducing feed value for dairy cattle during winter. Inside the harvester, the chopping drum rotated at high speed using multiple knives arranged to process grass or maize continuously. The drum accelerated crop material toward the blower system, which transferred chopped forage through the discharge spout into trailers driving alongside the machine. Maintaining uninterrupted airflow was essential. Wet material could still create blockages, especially during difficult seasons, but the Jaguar reduced many of the interruptions common with earlier pull-type machines. The design also carried limitations. Early self-propelled forage harvesters required careful maintenance and skilled operators. Knife sharpening, feed roller adjustment, and drivetrain servicing remained demanding tasks. Fuel consumption was significant compared with the smaller tractor systems, and repairs could become expensive for farms without dealer support nearby. But despite these drawbacks, the technical philosophy behind the Jaguar 60SF represented a major shift. For the first time, a forage harvester was not simply an attachment. It was an independent harvesting system engineered around productivity itself. The first farms to adopt the Claas Jaguar 60SF were usually larger dairy operations or agricultural contractors working across multiple properties. These early buyers were not searching for novelty. They were searching for survival in an industry where harvesting delays could destroy feed quality within days. Initial reactions were mixed. Demonstrations attracted attention because the machine worked differently from nearly everything farmers had seen before. The Jaguar moved through fields with a level of continuity uncommon for the period. Instead of stopping repeatedly to manage overloaded tractor systems or clogged intake channels, it maintained a more stable operating rhythm. For contractors paid by harvested area or tonnage, this difference mattered immediately. But enthusiasm came with hesitation. Many operators worried about reliability. Self-propelled forage harvesters contained more specialized components than traditional tractor and chopper combinations. A breakdown during peak silage season could leave large acreages exposed to bad weather with little time for repairs. Farmers also questioned whether mechanics in rural regions possessed enough experience to service such advanced equipment properly. The learning curve proved real. Operators had to understand feed rates, knife condition, and crop moisture more carefully than before. Driving technique changed as well. Maintaining efficient trailer loading while moving through uneven terrain required coordination between harvester and transport crews. Inexperienced teams sometimes lost efficiency despite the machine's capabilities. Yet results in the field began changing opinions quickly. Farms using the Jaguar 60SF often completed harvesting faster with fewer laborers. Silage consistency improved because the machine delivered more uniform chopping performance over long working periods. During narrow weather windows, that advantage could protect enormous quantities of forage from rain damage. Across parts of Western Europe, neighboring farmers watched closely. The Jaguar was no longer viewed as an experimental machine. It was beginning to look like a warning that traditional harvesting systems were approaching their limits. Real proof of the Claas Jaguar 60SF did not come from exhibitions or brochures. It came from difficult harvest seasons when fields turned soft, schedules collapsed, and farmers had only a few days to secure feed for entire herds before rain destroyed crop quality. In those conditions, the machine revealed why self-propelled forage harvesting represented more than a technological trend. Operators working long silage campaigns discovered that continuous throughput mattered as much as raw engine power. Wet grass and dense maize created enormous stress on feed systems. Older pull-type choppers frequently slowed under heavy intake, forcing tractors to reduce speed or stop entirely while material was cleared manually. The Jaguar 60 SF still faced hard conditions, but its integrated design improved operational stability. Dedicated traction and harvesting systems allowed operators to maintain steadier movement through soft ground. The elevated cab gave better visibility across narrow European fields, where trailers often traveled dangerously close beside the harvester during loading operations. Harvest crews began reorganizing around the machine's pace. Instead of waiting for the harvester, transport vehicles struggled to keep up with chopped material output. On larger farms, multiple trailers rotated continuously between field and silage bunker to avoid interruptions. The bottleneck in forage production was shifting away from harvesting itself toward transportation and storage logistics. Long operating days also demonstrated the physical demands of mechanized silage production. During peak periods, machines sometimes worked from early morning until late at night, while operators monitored knife wear, engine temperatures, crop moisture, and fuel usage almost constantly. Maintenance crews sharpened blades and serviced moving components between shifts to prevent costly downtime. The Jaguar did not eliminate difficulty from forage harvesting. It concentrated the entire operation into a faster, more industrialized process. And once farmers experienced that level of productivity, returning to slower systems became increasingly difficult to justify economically. As the 1970s progressed, machines like the Claas Jaguar 60 SF began reshaping the economics of livestock farming across Western Europe. What started as specialized equipment for large farms and contractors gradually influenced the entire structure of forage production. The speed of harvesting was increasing, but more importantly, the scale of possible operations was expanding alongside it. Farmers who once planned silage work around labor availability now organized entire harvest schedules around machine capacity. A self-propelled forage harvester could process far more material in a single day than many traditional systems operating with several tractors and multiple crews. This changed investment decisions across agriculture. Farms expanded herd sizes because they could secure larger quantities of preserved feed within narrower weather windows. Agricultural contractors became especially important during this transition. Many medium-sized farms could not justify purchasing a dedicated forage harvester outright, but contractors operating Jaguar machines offered access to high-capacity harvesting without full ownership costs. In some regions, contractors effectively industrialize silage production by moving rapidly from farm to farm during harvest season. Manufacturers across Europe noticed the shift immediately. Competitors accelerated development of their own self-propelled forage harvesters with improved chopping systems, stronger drivetrains, and larger headers. The market was no longer experimenting cautiously. Self-propelled forage harvesting was becoming a strategic category within agricultural machinery production. The effects extended beyond machinery sales. Better silage consistency improved livestock nutrition, especially in dairy operations dependent on reliable winter feeding. Larger feed supplies supported higher milk production and encouraged further intensification of animal agriculture. Entire supply chains adapted around greater forage efficiency. By the end of the decade, the basic philosophy introduced by early Jaguar machines had already changed expectations permanently.
Farmers no longer measured harvesting success simply by finishing the field. They measured it by how much material could be processed before weather, labor shortages, or mechanical limits stopped the system. The rise of machines like the Claas Jaguar 60 SF created clear winners and losers across the agricultural machinery industry. Companies able to adapt to high-capacity forage systems expanded rapidly. Those dependent on smaller pull-type equipment increasingly lost relevance as farms demanded greater productivity and shorter harvesting windows. For traditional manufacturers, the transition was expensive. Self-propelled forage harvesters required advanced driveline engineering, stronger transmissions, improved hydraulic systems, and more specialized dealer support networks. Smaller firms often lacked the financial resources to compete in this new environment. Some disappeared entirely through mergers or bankruptcies. Others survived only by focusing on niche equipment categories outside large-scale silage production. Meanwhile, major agricultural manufacturers intensified competition aggressively. Engineers worked to improve chopping precision, fuel efficiency, operator comfort, and crop throughput. Cab visibility became better. Headers widened. Engines grew more powerful. By the late 20th century, forage harvesters had evolved into highly specialized machines capable of processing enormous volumes of maize and grass within extremely narrow seasonal windows. The broader agricultural impact was equally significant.
Reliable high-speed forage harvesting encouraged larger dairy and livestock operations throughout Europe and eventually other parts of the world. Farms became more mechanized and increasingly dependent on coordinated logistics involving harvesters, transport vehicles, silage bunkers, and feed management systems. The old image of silage production as slow, seasonal labor was disappearing. But industrialization carried consequences. Smaller family farms struggled to match the efficiency of larger operations using advanced harvesting equipment. Capital costs rose steadily. Agriculture became more technologically dependent and economically concentrated. Even so, machines descended from early Jaguar concepts helped stabilize feed production for millions of animals worldwide. Consistent silage availability supported expanding milk and meat industries that fed rapidly urbanizing populations during the second half of the 20th century. The machine itself was never the entire revolution. It was the mechanism that accelerated a much larger transformation already beginning inside global agriculture. Decades after the first Claas Jaguar 60SF entered European fields, the logic behind its design still remains visible across modern agriculture. Today's forage harvesters are larger, faster, and vastly more computerized, but they continue following the same industrial principle introduced during those early years: uninterrupted crop flow, maximum harvesting efficiency, and complete integration between machine power and feed production. On modern dairy farms, silage harvesting operates with a level of precision that earlier generations could barely imagine. GPS guidance, yield monitoring, automatic kernel processing, and advanced feed analysis systems now support operations covering enormous acreages. Yet, beneath those technologies lies the same pressure that originally created the Jaguar 60 SF: the need to secure massive quantities of forage within extremely short seasonal windows. The machine also changed expectations about agricultural labor itself. Before self-propelled forage harvesters became widespread, silage work demanded large groups of workers performing physically exhausting tasks under unpredictable conditions. Mechanization did not remove hard work from agriculture, but it dramatically shifted the balance from manual labor toward machine coordination, logistics, and technical management. Many early Jaguar units disappeared long ago through wear, corrosion, or simple replacement by newer generations of equipment. Some surviving collections or smaller farms remembered as transitional machines from a period when agriculture moved decisively toward industrial-scale production.
To modern operators, their capacities may appear modest, but during their era, they represented a major break from traditional harvesting limits. The transformation they helped create extended far beyond machinery sales or farm efficiency statistics. They contributed to a system capable of supporting larger livestock populations, expanding dairy industries, and increasingly urban societies dependent on reliable food supply chains. In quiet fields, where forage harvesters still move beside endless trailers every summer, the influence of the Jaguar 60SF has never completely disappeared.